Every day, thousands of modern jet airliners cross the sky. The passengers sitting inside mostly see the simple things: the seats, the windows, the wings, and the clouds drifting outside. But behind that calm cabin, a hidden machine is working non-stop. This aircraft is not just flying through the sky. Its body has to hold pressure high above the ground. Its wings do not only create lift, they can store fuel, control airflow, and help keep the aircraft stable from takeoff to landing. The engines create thrust, but the whole aircraft is kept alive by many invisible systems: electricity, hydraulics, air management, water, waste, safety systems, and emergency backups. Everything is working together while this massive machine moves far above the ground at hundreds of miles per hour. So in this video, we are going inside the simple aircraft we see from the outside, system by system, to understand how a modern jet airliner actually works. And to understand that machine, we have to begin with the body itself, because an airliner is not just a cabin with wings. It is a flying pressure vessel. What looks like a simple metal tube is actually one of the most important survival systems on the aircraft. The fuselage is not just a space for seats, aisles, overhead bins, and passengers. At cruise altitude, it becomes a sealed structure holding back a world humans were never built to live in. Outside the aircraft, the air is thin, cold, and low in pressure. Inside, people are breathing, drinking coffee, watching movies, and walking down the aisle as if they are still close to the ground. That only works because the airframe carries pressure from the inside, while handling the forces of flight from the outside. Under the smooth aircraft skin, there is a hidden skeleton. Frames give the fuselage its shape. Stringers help carry loads. Ribs and structural members support the wings and control surfaces. Together they deal with bending, vibration, temperature changes, and repeated pressurization cycles, flight after flight. Even the windows are part of this engineering. They are small, rounded, and carefully shaped, because sharp corners can concentrate stress. What looks like a design choice is really a safety choice. And below the passenger floor, the aircraft becomes even less like a normal room. Under your feet, there may be cargo, wiring, ducts, pipes, control lines, and other systems moving through the body like hidden veins. The cabin is only the visible layer. The airframe underneath is the foundation that holds the entire flying machine together. But this strong body does not lift itself into the sky. To understand how an airliner stays airborne, we have to move outward, to the wings. From the window seat, the wing can look like a quiet piece of metal, stretched out into the sky. But the wing is not passive. It is a carefully shaped air machine, built to turn forward motion into lift. As the aircraft moves, air flows around the wing, above it and below it. The shape of the wing guides that airflow, creating the force that carries the aircraft's weight. Not just the passengers, but the fuel, engines, structure, and the entire flying machine. But the wing does not stay the same through the whole flight. During takeoff, slats at the front and flaps at the back change the wing's shape, helping it produce more lift at lower speed. Once high in the sky, those surfaces retract. The wing becomes smoother, cleaner, and more efficient. Then, as the aircraft prepares to land, the wing changes again. Flaps extend, spoilers may rise, and the same surface that once helped the aircraft climb now helps it slow down and descend with control. The pilot is not just holding the aircraft up with the wing. The pilot is controlling how the wing behaves. Ailerons help roll the aircraft. Spoilers can disturb airflow. Flaps and slats reshape the wing for different phases of flight. And inside the wing, there is even more hidden engineering. Structural beams carry enormous loads. Fuel space may be built into the wing itself. Control systems run through it, waiting to move surfaces with precision. So the wing is not a fixed object. It changes its behavior from takeoff to cruise to landing. But lift alone is not enough. The aircraft must keep moving forward through the air, and that job belongs to the engines. Yet on a modern jet airliner, an engine is far more than something that simply pushes the plane forward. Look out at the engine from a window seat, and it may seem like the simplest part of the aircraft. A huge spinning machine hanging under the wing, making noise and pushing the plane forward. But a modern turbofan engine is doing something far more complex than that. At the front, the fan pulls in a massive stream of air. Some of that air goes into the engine core, where it is compressed, mixed with fuel, burned and sent through turbines. But much of the air does not pass through the burning core at all. It moves around it as bypass air, and that large flow creates a major part of the engine's thrust. This is why the engine is not just a fire tube. It is an air-moving machine. The fan, compressor, combustion chamber, and turbine work in a continuous chain, turning air and fuel into the power that pushes the aircraft forward. But the engine is also connected to the rest of the aircraft. Engine-driven generators can supply electrical power. On many airliners, air taken from the engine system can also support pressurization, air conditioning, anti-ice protection, or engine starting. Not every aircraft uses this design, but the engine can still be part of a hidden support network. So when passengers hear that deep engine sound, they are not only hearing thrust, they may also be hearing one of the aircraft's main power sources, feeding systems that help the cabin stay controlled, pressurized, and protected. The engine keeps the aircraft moving, but it cannot do anything without a carefully managed supply of fuel. And inside a modern jet airliner, fuel is not just stored in a simple tank. It affects weight, balance, range, and the way the aircraft behaves in flight. Inside the wing, beyond the smooth metal surface passengers see from the window, there is often something unexpected: fuel. On many modern airliners, much of the fuel is stored inside the wings themselves, and depending on the aircraft design, some fuel may also be carried in center tanks closer to the body. This is not just a convenient place to put it. Fuel has weight, and on a large aircraft, that weight is enormous. Placing fuel in the wings saves space, but it also becomes part of the aircraft's balance and structure. But the fuel does not simply sit there until the engines need it. Pumps, valves, sensors, and fuel lines manage the flow. Fuel has to move from the tanks to the engines at the right rate, through climb, cruise, turns, and descent. As fuel burns, the aircraft becomes lighter, and its balance and performance gradually change. On long flights, fuel planning is part of safe and efficient operation. The wings hold the aircraft up, but in many airliners, they also act like flying fuel tanks. And once that fuel reaches the engines create motion and power. But to wake up the silent systems inside the aircraft, the machine needs something else moving through it: electricity. A modern jet airliner can look powerful because of its engines, wings, and size. But without electricity, much of that machine would become blind, silent, and unable to coordinate itself. Electricity moves through the aircraft like a nervous system. It does not create lift or push the airplane forward, but it lets hidden systems wake up, communicate, and respond. Cockpit displays, sensors, pumps, lights, radios, navigation equipment, warnings, cabin systems, and flight computers all depend on it. Once the engines are running, engine-driven generators can supply electrical power to the aircraft. But before that, when the aircraft is still on the ground, a smaller machine can help bring everything to life. Hidden in the tail, the Auxiliary Power Unit, or APU, can provide ground power and support other systems before the main engines take over. That is one of the quietest reveals inside an airliner. Sometimes, the first real power comes from a small unit in the tail, turning a dark cabin and quiet cockpit into an active aircraft. From there, electrical power is distributed through buses, sending power to different parts of the airplane. If one source is lost, another source can often support essential systems. Batteries add another layer of emergency backup, keeping critical equipment alive when needed. This is why the cabin can feel so calm. Behind the walls and panels, electrical pathways are constantly feeding the systems that passengers barely notice. Once electrical power is flowing, the aircraft begins to think in a different way, not like a human, but like an alert network of instruments, sensors, computers, and warning systems. In the cockpit, the pilots are not just looking out the window, they are looking at the aircraft's condition in real time. Altitude, airspeed, engine performance, fuel status, navigation position, and system warnings are all being collected and displayed, turning the aircraft's condition into information the crew can use. Behind that information is avionics, the electronic brain of the aircraft. Sensors feed computers. Navigation systems help the aircraft know where it is. Communication links connect the pilots to the ground. Weather radar and warning systems watch for risks that may not be visible from the cabin or cockpit window. The flight management system can help plan the route, estimate performance, manage navigation and support fuel planning. But it is not magic, and it does not make the aircraft independent. It works with information entered, checked, and managed by the pilots. The same is true for autopilot. Autopilot does not mean the plane is simply flying itself while everyone sits back. It follows selected commands. It can hold altitude, follow a route, control heading, manage climb or descent, and fly with incredible precision. But it is still supervised by the crew. That is the hidden reveal. Autopilot is not the pilot's replacement. It is a precision tool, following instructions inside a much larger brain. But thinking is not the same as moving. Once the aircraft decides what needs to happen, something still has to move the giant surfaces outside. That job belongs to the hidden muscle of the aircraft, the hydraulics and flight controls. The pilot may move a control yoke, a side stick, or a set of pedals with only a small motion. But outside the aircraft, the surfaces that respond to those commands are enormous. Ailerons move on the wings. Elevators move at the tail. The rudder shifts the aircraft's nose. Spoilers rise into the airflow. Flaps extend for takeoff and landing. Even the landing gear may depend on powerful systems to move into position. No human hand could move those heavy surfaces directly against the force of the air. This is where hydraulics become the hidden muscle of the aircraft. Hydraulic systems use pressurized fluid to transmit force. A small command can become a powerful movement, strong enough to shift large control surfaces with precision. The pilot gives the input, but the hidden system does the heavy work. On many modern airliners, that input may not go straight from the pilot's hand to the surface. In fly-by-wire aircraft, the pilot's command is interpreted by computers first. Those computers look at the aircraft's speed, attitude, configuration, and flight conditions. Then they help send the right command to actuators, which move the surfaces outside. It is a chain of control. The pilot commands, the computers process, the hydraulic system provides force, the actuators move the aircraft's surfaces, and the airplane responds, not roughly, but with measured precision. This is also why redundancy matters. A jet airliner cannot depend on one single path to control the aircraft. Multiple hydraulic systems, backup logic, and separated components are designed so that one failure does not automatically mean loss of control. Flight control is not just steering. It is stability, balance, lift, drag, and precision, all being adjusted while the aircraft moves through invisible air at high speed. But controlling the aircraft is only one part of the machine. While these surfaces move outside, another invisible system is working inside, keeping people alive at 35,000 feet. That system is air management. At cruising altitude, the aircraft is flying through a place where the human body cannot simply survive. The air outside is thin, freezing, and far too low in pressure for normal breathing. From the cabin, it may feel like a comfortable room in the sky, but that comfort is being created artificially, moment by moment. Inside the aircraft, cabin pressure is carefully controlled, so passengers and crew can breathe without thinking about it. The aircraft is not pressurized to sea level, but it is kept within a range the human body can tolerate. That invisible pressure is why people can sit, sleep, eat, and talk, while the airplane crosses the sky at high altitude. Temperature is controlled too. The air entering the cabin has to be conditioned, cooled, or heated, mixed, and distributed through ducts, so the cockpit and cabin remain usable. This is not only about comfort. Electronics, crew performance, passenger safety, and the entire cabin environment depend on controlled airflow. On many airliners, air from the engine system can play a role in pressurization and air conditioning, but not every aircraft uses the same design. Some aircraft rely more heavily on electric systems. The exact architecture can change, but the purpose remains the same. The airplane must create a livable atmosphere inside a metal body flying high above the ground. If pressure drops, oxygen masks become part of the emergency layer, giving passengers backup protection when the cabin environment changes. Outside the cabin, ice protection helps protect exposed surfaces and engine areas from dangerous buildup, because ice can disturb airflow and create risk. This is the hidden reveal. A jet airliner is not only flying through the atmosphere, it is creating its own controlled atmosphere inside. But the aircraft does not stay in the sky forever. Every flight ends with a return to the ground, and that moment puts the machine through one of its hardest physical tests: landing. Landing is the moment when a flying machine has to become a ground vehicle again. For hours, the aircraft may have been supported by air, moving smoothly above the clouds. Then, in the final seconds, all of that weight comes back to the runway through a few sets of wheels. The landing gear is not just a collection of tires. It is a shock-absorbing system built to handle one of the most physical moments of the entire flight. At touchdown, the gear must take the impact, support the aircraft's weight, and keep it stable as the wheels spin up from 0 to runway speed almost instantly. The tires handle extreme loads. The struts absorb energy. Doors, actuators, sensors, and locks work in sequence as the gear extends for landing and retracts for clean flight. Once on the runway, stopping the aircraft is not the job of one system alone. Brakes absorb enormous energy. Spoilers rise on the wings to reduce lift and put more weight onto the wheels. Reverse thrust can help slow the aircraft, depending on the aircraft and landing conditions. The reveal is that the wheels touching the runway are handling the aircraft's most violent transition, from air to ground. But even after that impact, the machine is not finished. Inside the cabin are systems passengers barely think about: water, waste, fire protection, emergency lighting, oxygen, and backups that quietly support the entire operation. After the aircraft slows down and leaves the runway, the hidden machine is still working. Some of its systems are not dramatic from the passenger seat, but they are part of what makes the aircraft usable, safe, and complete. Water has to be stored, moved, heated, and delivered. Waste has to be sealed and contained inside a moving aircraft, where even simple cabin systems must work under pressure, at altitude, and within strict weight limits. Then there are the systems that passengers hope they never need. Fire detection watches critical areas. Fire suppression can respond where fire would be most dangerous. Ice protection helps protect exposed surfaces and engine areas from ice buildup. Emergency lighting can guide people through smoke or darkness. Oxygen systems can support passengers during pressure problems. Backup power and redundant systems are there because a modern airliner is not designed around one single path to safety. That is the real story of a jet airliner. It is not one machine doing one job. It is a network of systems, each one supporting another. The airframe holds pressure. The wings create lift. The engines create motion and power. Fuel, electricity, avionics, hydraulics, air management, landing gear, and safety backups all work together behind the calm cabin. So the next time you sit by the window and the flight feels quiet, remember what is hidden around you. A modern jet airliner feels simple because thousands of hidden processes are working at the same time without asking you to notice them. If this journey changed the way you see an ordinary flight, leave a like, share your thoughts in the comments, and subscribe for more deep visual breakdowns of the machines that shape our world.